Okay. Formal Lab 2 resistive force, Group 6B. Our research question is, how does changing the surface area of an object impact its velocity and resistive force experienced while falling? Our goal is to gain a better understanding of the relationship between velocity and resistive force, also known as air drag. And our findings for this experiment was a smaller surface area accounts for a smaller terminal velocity, which ultimately equals a lower drag constant.
Background information. Drag force is defined as the force opposite of gravitational force when an object is dropped in the air. Many factors impact this value, and we will get to this in the next slide. While the object falls in the air, the velocity increases due to the gravitational force being greater than the drag force initially. However, at a certain point, the forces are equal to each other, and the object will reach a constant velocity that is otherwise known as terminal velocity. Here is a drag force equation. As you can see, there is a drag coefficient value, which is constant. The density of fluid, which in our experiment is the air, the surface area of the object, and the velocity of the object that is traveling in the air. In our experiment, the only variable that we changed was the surface area. Here are the models for this experiment. Starting with the system schema. The system includes air, the origami, and the earth. The force diagram shows the forces that are acting on the origami, which is the drag force we just discussed, and the gravitational force. It is important to recognize that these two arrows are equal at terminal velocity. And then, just as a refresher, energy is neither created nor destroyed and changes from one form to another. This slide shows the energy pie charts from when the origami is dropped, where it is only potential energy, halfway down, where it is half potential energy and half kinetic energy, and then when the origami hits the ground, which is almost all kinetic energy. We can also look at the equations to understand the change. So since mass is constant, we can ignore this for now, and this only leaves the velocity and the height as the only changing variables in our experiment. We can conclude that as the height decreases, the velocity increases to balance out the energy in the equation.
For experimental design, we used origami papers so that we were able to keep the mass of our 3 trials constant while using surface area as our independent variable. We did this by folding 3 different origami designs, each with a different surface area. We then dropped each origami from the same height while recording, and then used Tracker to measure the position, time graph, and velocity and acceleration time graphs. Here are 3 different experimental shapes, each with a different surface area. Here is our data analysis from Tracker. These are our 3 different position time graphs. The line best fit represents the average change of position and time during the terminal velocity period. And from there, we were able to use the slope of this line to find the terminal velocity of each origami. We were also able to calculate using Tracker the standard error for each origami as well. Continuing with our data analysis, because the acceleration during terminal velocity is equal to 0, we know the net force is equal to 0, while also being equal to force drag plus gravitational force. So we were able to set negative force of gravity equal to force of drag. And from there, by using our constant mass and the acceleration of gravity, we could calculate the force of gravity and therefore the force of drag for all 3 trials. And then using our known values, we were able to calculate the drag constant for each of the 3 origami pieces. The overall force was 1.47 times 10 to the negative 5th newtons, and the drag constant for the fox was 2.58 times 10 to the negative 5th. For the jack-o'-lantern, 1.14 times 10 to the negative 5th. And for the scarab, 2.51 times 10 to the negative 5th.
Our experimental data was compared to a simulation using a glow script code. This is the Paraseum code from class that was modified to fit our experiment. These graphs show what the position, velocity, and acceleration should look like if we had no errors in our experiment. It is also important to notice that these values are not the same as our actual experiment and is only theoretical.
So the standard error for origami fox is plus or minus 0.04. The standard error for origami jack-o'-lantern is plus or minus 0.02. The standard error for origami scarab is plus or minus 0.04. Some things that could have impacted error are a draft in the classroom could have impacted the velocity of the falling origami. and small errors from the camera could have impacted tracker. In conclusion, smaller surface area indicates smaller drag constant and smaller terminal velocity.